Hello and welcome to Lesson 6. Before we get started, make sure you have your math book out and turn it to page 48. You'll need a pencil and calculator. All right, let's get started. Today's lesson is called Using Equations to Solve Problems. And we're going to use those equations to help us solve problems involving proportional relationships, just as we've been doing in the past few lessons. Our goals for today is we're going to be able to relate all of the parts of the equation, like y equals kx, to the situation it represents. Now remember, k is our constant of proportionality. We're going to be able to find missing information in a proportional relationship using that constant of proportionality. Our first problem today is going to be all about concert ticket sales, and we're going to be calculating the cost of tickets. So our first problem reads, and you should be on page 48, a performer expects to sell 5,000 tickets for an upcoming concert. They want to make a total of $311,000 in sales from these tickets. So assuming that all of the tickets have the same price, what is going to be the cost for one ticket? Now, in order to do that, we really need to think about the cost per ticket. Sometimes people want to think about tickets per cost, but the true proportionality unit rate here is cost per ticket. So we know we have $311,000 for a total of 5,000 tickets. And if we want to know the cost per ticket, we take our calculator and type in the 311,000 and divide it by 5,000 to find our unit rate or cost per ticket. And we find that it comes to 62.2. Now, because this is money, it's $62.20 per ticket. In the unit leading up to this, we worked all with proportions and finding unit rates. So we just solved number 1. Now we just discovered that it's $62.20 if we sell 5,000 tickets. Now question 2 is asking, well, what happens if you sell 7,000 tickets? Well, I like to keep my unit rate in mind, so don't forget, one ticket is $62.20. I'm going to write that per ticket up here on the top. Now, what are you thinking we should do in our calculator? There's something we need to type in. We are going to type in the cost for one, $62.20, and we're going to multiply it by the number of tickets we want to sell, times 7,000. Again, with our calculator, if you type that in, 62.2 times 7,000, you're going to come up with $435,400. That is a lot of money to take in after selling 7,000 tickets. You might want to hit pause and record this on number 2, and then we'll move on to number 3. Alrighty. Number 3 says, a performer expects to sell 5,000 tickets. Oh, that's our just ongoing problem. Don't mind me. So now we need down here on the side, we want to find out the cost for 10,000 tickets, 50,000 tickets, 120,000 tickets, 1,000,000 tickets, and X number of tickets. And you'll see that those are all on number 3. I'm going to model 10,000 tickets and X number of tickets, and I'm going to let you do on your own in your calculator 50,000, 120,000, and 1,000,000. So don't forget, we have our unit rate, which is $62.20, and we're going to multiply that by 10,000, our number of tickets, price per ticket times number of tickets. And when I type that into my calculator, I come up with $622,000 that they would take in after selling that many tickets. Now before, when we had 5,000 tickets, I did my 7,000 tickets. I had $62.20 times the 7,000, and we found our answer. And just like if this was on a table, if I wanted to know X number of tickets, I would type my 6220, and it's just going to be times, I'll put a dot here so we can tell the difference, times X. Now, as you can recall from our last unit, we know that this becomes 62.20x. That's what it means. So for any number of tickets, which represents our X, we can just multiply it by 6220 and we'll find out how much money we have. Now, before I go on to the next slide, I want to make sure that as you're recording your information here, you write down all of your equations so that you can go back and check your work later on. And here we go for the next one. Continuing on with the same situation, now we're looking at if we have a certain amount of money that we want to make, how many tickets can we sell? Well, don't forget that we know each ticket we need to sell for $62.20. So I know that I've got to make $379,420. And I know that has got to be our $62.20 times some amount, but we don't know what that amount is. So what on earth could we do? Well, back when we had a simpler equation, for example, let's pretend this was, we wanted to make $12 and we knew it was going to be 3 times some number was 12. In our calculator, we would type in 12 divided by 3 equals 4. That's something that we know. And we've likewise done that on tables all along. So even though these numbers are larger, we're still going to do the same thing. So I'll type in the 379,420. I'll divide it by 6220. And I'm going to discover that X, my unknown number of tickets, is 6,100. So I've got to sell 6,100 tickets in order to make this much money. So that was number 4. Make sure you record that equation. You don't need to record this at the top, but please record the rest. And we'll move on. The next one, it's the same situation where I have to figure out how many tickets I need to sell to make 5 million. I will model the equation here, but I'd like you to solve it on your own. But we've got our $5 million here that we would like to make. And we know we have to do $62.20 times what number to find out how much we make. I'm going to let you type that into your calculator and write it down on number 5. And we'll move on to our next problem. Feel free to hit pause and record all of your answers. So what's interesting here, it says, what are some equations we found in this lesson? And I just wanted to take a quick moment and relate this to the constant proportionality equation, where y equals k, which is our constant, times x. And in this situation, our x was the number of tickets, and the y was how much money we made. So the equation for this was simply y, meaning total amount of money, equals $62.20 times the unknown number of tickets. So we knew the number of tickets in some of our problems where we just multiplied $62.20 by that amount. And we also had a couple of problems where we knew the total amount of money that we wanted to take in, and that's where we did the division to find out our answer along the way. So that is what we know so far about equations in this problem. What I want to do is reflect for a moment on our goals for today. And our goals include relating parts of our equation, like y equals kx. The y equals kx we just did in our problem about ticket sales. And we're going to continue to practice some of these in the practice problems coming up. So as we go through this, it will become easier and easier to find this information. But I really think we are making great progress. So let's continue to the practice problems. Let's start with number 1. And to find this problem, you'll want to go in your book to page 51. I will move to mine as well. Practice problem number 1 says, a car is traveling down a highway at a constant speed described by the situation d equals 65t, where d represents the distance in miles that the car travels at a speed in t hours. So the question is, what is the 65 representing in this problem? Well, if I'm thinking about a car and how fast it's going, and we think about our real life situation, what might 65 mean? Well, 65 means 65 miles per hour, how fast this car is going. So I could write it as 65 mph, which is the shortcut for miles per hour. You could also write it out. We also know that it goes 60 miles per hour means in 1 hour. So for every hour that you travel, it goes 65 miles. So now we're being asked, how many miles can the car travel in 1.5 hours? And what I'm going to do is I'm going to write down that equation again, d equals 65t, and t, don't forget, represents time. So instead of a t, I'm going to replace that with the 1.5. So I'm going to say d equals 65 times 1.5, because 65t means the same thing as 65 times t. So in my calculator, I'll do 65 times 1.5, and that tells me that d equals 97.5. Well, in the context of this problem, this 97.5 is how far it's traveled in miles. So we have gone 97.5 miles in an hour and a half. The last question is, how long does it take the car to travel 26 miles at this speed? So what I always like to do is start with my equation again. So I'll write that again. D equals 65t. And this time, instead of knowing the amount of time, I know my distance. So I'm just going to plug these numbers right in. So instead of writing d, I'm going to write 26 equals 65 times t. Or I should write that a little differently so we can kind of think it out. 65 times t. Now remember, we've done this before. I know that 65 times some number is 26. So to undo that, in my calculator, I'm going to type in 26 divided by 65. And that gets me t equals 0.4. Time is 4/10 of an hour, is what that essentially means. And I know that if I break my hour, my 60 minutes, into tenths, 1/10 of that hour is 6 minutes, because there's 6 tens in 60. So if 1/10 of my hour is 6 minutes, 4/10 of my hour is going to be 4 of those, so 24 minutes. I guess that gives us a better context of exactly how much how time this is taking to travel. I'm going to work with you on number 2, and then practice problems 3 through 5 I'm going to have you do on your own. But here is our next one. Elena has some bottles of water that each hold 17 fluid ounces. Write an equation that relates the number of bottles, B, to the total volume of water, W, in fluid ounces. Well, before I do something like this, I like to start in with a table that really kind of helps outline what's going on in this situation. So let's take a look. If I have B for bottles, my table, and I've got W, this is just instead of X and Y. W is the total amount of water. Let's fill in some values that we know, and perhaps we can come up with a constant of proportionality that can help us figure out these larger numbers. So I know that she has some bottles that each hold 17 fluid ounces. So I'm going to assume that means one bottle is 17 fluid ounces. Let's say 2 bottles would be 34. And what I've done is I've discovered my unit rate, right? I know that 1 times 17 becomes 17. 2 times 17 becomes 34. Let's do 3. 3 times 17 is 51. And in our previous lessons, we have discovered that this number that we're multiplying by every single time is our constant of proportionality. Shortcut K is constant, and our constant is 17. And what that 17 stands for is from our original 1 per our unit right here, 17 ounces per every 1. So, how much water is in 51 bottles? Well, this is deceiving, right? Because we've got this 51 here, and you'd assume that we're done, but we're not. We just found out that 3 bottles have 51 ounces, but we need to go backwards. So, if I had 51 bottles instead, what would I need to do to find out how much water? Well, the nice thing is I use that constant proportionality just like with our table, and I know that to go from bottles to water, we need to multiply by 17. So 51 times our 17 is 867. Oops, I wrote 4. 867 ounces of water. I'm going to put this in an equation where we knew that W equals our 17 times our bottles of water. So there's the equation of what this is. And the last question, C, says how many bottles does it take to hold 51 fluid ounces of water? Well, we already found that one coincidentally here in our table. So we discovered that that is 3 bottles hold that much. So today we have practiced some context problems of the constant of proportionality and how we can use the equation to help us solve things. I also highly recommend a table. Don't stray away from this table. I really think it helps us understand. For the remaining time today, I'd like you to practice and finish up the practice problems. And please don't hesitate to reach out if you have any questions. Thanks and have a great day.